All right, and what procedure should I use for this one?
One sample
T interval.
for mu.
Okay, let's check our conditions.
Don't we have to define mu?
Oh, yeah. Where mu equals the true mean nitrogen oxide level. For light duty engines or something like that. Okay, what else? Now can we check our conditions? All right, what's the first one?
Right.
And how we doing?
Given.
What was given? How was it given?
Random sample.
Okay, normal? N equals 40, which is in fact greater than 30. Cool. Independent?
40, like the
40 is less than 10% of light duty engines. Does this feel reasonable?
yes.
Everybody good? All right, what's next? Is there anything else that needs to go in that left side box? No, so it's time to do our calculations. Reminder, your rule of thumb is anything you have to tell the calculator, you have to tell to me. So, what should we do? Huh? Okay, how many degrees of freedom do we have? 39, okay. And basic summary statistics is X bar is 1.267 and S is 0.3332. Then what? Then we go to the calculator. So I'm going to hit stat. I'm going to go over to tests. Which one should I pick? Stats, test,
T. Oh, I meant like the T interval.
T interval. Okay. And this time, do we have the raw data? No. So what you're going to do is up where it says stats, you want to make sure the stats is highlighted this time. And then you can put in all the information it's asking you for. So let's see. We got X bar is 1.267. 0.3332. $40 and 95%. Go down to calculate. Everybody feeling okay? And we get 1.16 to 1.37. Heckle.
Huh?
I'm heckling.
Okay.
You guys didn't chat about wearing that sweatshirt today?
Oh, no. I was like, again? No.
All right, y'all. We have our interval. What's next? Conclusion. So, tell me the conclusion.
We are 95% confident that the interval from 1.16 to 1.37 contains the true mean of an influence.
See, this isn't bad. And Nico, I have been recording.
Okay.
And I'll put the recording up on Schoology while you guys are working the second half of class.
Thank you.
All right, next. The EPA sets a limit of 1 gram per mile for NOx emissions. Are you convinced that this type of engine is 1.0 or less? No. Are we convinced of anything else?
It's greater than.
Yeah, we're convinced. It's more than 1 gram per mile because the entire interval is greater than 1. Are we already feeling more confident than we did for the last test? Okay, now, we got to go way, way back. Okay, we kind of talked about 3 major types of experimental designs. Those 3 were completely randomized, the second was called randomized block. And the third one was called a matched pair. So I might as well take this opportunity to review each of those kinds, okay? For the completely randomized design, what happened is you had your participants in the study, you randomly assigned them to treatments, and that was it, okay? It was the most basic form of a experimental design, okay? A randomized block design is you said, hey, I know this one thing is going to be a lurking variable, so I'm going to kind of break my participants into blocks first, and then randomly assign treatments to each block so that confounding variable is present in both treatment groups. Okay? Does anybody remember what the matched pairs design was?
Like twins.
Twins could have been considered, a twin study would be a matched pair design. If the same person received both treatments, that would be a matched pairs design. Okay? And so it's when each data point is a difference between two other data points. I'm going to say is the difference between two observations. I think that's the easiest way to say it. So, for example, if there was a twin study, we'd have two observations of the twins, but the actual data point is the difference between the two twins. Does that make sense? Okay. Is that the only way we can have? So that creates something called paired data. Okay, where each data point comes from a pair of two observations. Okay. So paired data is two observations become one difference, and that those differences, each individual difference is what you're looking at. Okay, some other types of studies before and then after studies would be paired data, even though it wouldn't be a matched pairs design, because you wouldn't be randomly assigning people to do the before first and the after second, right? And it turns out that if you're doing this, you still end up with one sample. But anyway, I want to give you an example of something called a paired t-interval, which mathematically is going to look identical to a regular t-interval. Okay? So let's go ahead and say I gave a pre-test and a post-test. All right? And people's score on the pre-test was as listed here. And so this is student A, student B, student C. Like each of these columns represents a different student. Okay? And so what we might want to do to decide did the students improve is look at the differences for each student. Okay. So, for example, this first student, student A, how much did they improve? 2. The next student?
3.
The next student?
2.
Do you guys catch my drift here? Oh man, I wasn't very good at this. Who knew I couldn't subtract? That feels better. Okay, you guys. Do you guys see that for each student, the actual measurement is the difference in how much they grew, right? That's what Ms. Meister would want to report out to Mr. Belk. Okay, so so this would be an example of paired data. Do we have 2 samples here?
Well, that's just one.
It's just one sample. It's just that each participant in that sample has 2 values. That's what makes this a paired test. Okay? This is not a 2-sample test. Okay. All right. So we are going to estimate a different kind of mean now. We are going to do something called a paired t-interval for mu d, the mean of the differences, where mu d equals the true mean difference I can spell difference. After, and we're doing after minus before, of students' achievements. from here, you guys, I want to talk about the conditions a little bit more. Is the random condition met?
Yes.
Because?
Yeah.
There's a random sample. You were given that it was a random sample. Yeah? What about the normal?
We have to construct a graph.
We have to construct a graph. Now, to construct that graph, okay, when it's 15 students, you should still do probably a dot plot. Okay, if it was a little bit more than that, especially because we have to put this raw data into our calculators anyway, okay, we would need to, we could probably get away with doing like a box plot that the calculator makes, okay, but this is a small enough set that we can do this. And when you think about even my axis, it's going to be pretty easy. It's going to go 2, 3, 4, 5.
So just to confirm, we could not like put these in the calculator and get a graph from that and then just like say the graph was.
No. One to algebra 2. Probably 1 to the CC plus and 1 to math modeling. All right. Everybody good? Independent? We're going to say 14 is less than 10% of Meister students. It's probably not true, but we're going to pretend, okay? Okay. All right. Next, what do we need to do?
Define the degrees of freedom.
Okay, my degrees of freedom would be 14.
And then put these in the calculator.
Yep, so I'm going to let you guys put these into the calculator. A reminder to put the list in. You hit stat and then edit.
Are we doing the differences or?
The differences.
Okay. before 7.4, like that's not on our quiz, right?
Correct. And honestly, neither is the paired stuff.
Oh.
But we have the time for it, so I'm going to do it.
No, it's on Thursday. We're reviewing today.
Bless you. All right, y'all. What are we getting?
We got, well, for the mean, 3.133, and for the standard deviation, 0.9904.
And
The
the
interval, 2.5849, and 3.68.
and I would probably write n equals 15 as well. What do you guys think about this? Is this okay? Okay. And for our conclusion, we are 90. Was it 95?
Yeah.
Contains the true mean difference in post-test minus pre-test scores. So, can we say that the students improved? Because it's all positive, yeah?
Yeah.
Is this feeling okay? All right.